Here is my short description of intermolecular forces. So the weakest intermolecular force is the London dispersion force. And these are present in all molecules, but in nonpolar molecules, the London forces are the forces that are really going to be the ones that are predominating. So here we have a nonpolar molecule. Look how symmetrical these ethane molecules are. That means they're probably not polar. Now, all three of these intermolecular attractions, hydrogen bonding, London forces, and dipole-dipole attraction, are all the result of polarity. So if this molecule isn't polar, how does it have intermolecular attractions? Well, even though it's not really polar, it kind of becomes slightly polar just because of its electrons fluctuating from side to side. So at one instant, our ethane molecule on the top might find itself having more electrons on the right side, just for an instant. So we could draw a little dipole moment arrow to the right side to indicate that at this one instant, it has just a very slight dipole moment to the right. And that will induce a dipole moment in the other direction in this neighboring ethane molecule. Because its negative charge, its electrons, will want to go toward the left side. So for just an instant, we'll have a partial negative charge where the electrons went on the right side of the upper molecule, and we'll have a partial positive charge on the left side, and the opposite partial charges on the bottom ethane, and these opposites kind of attract. So this London attraction is kind of weak, but the bigger a molecule is, the stronger the London forces are going to be. So if this was a long chain, we would have more attraction between the two molecules because of more London dispersion forces. Okay, so check out this molecule. Here we have some asymmetry, yeah? I mean, we have fluorines on one side, hydrogens on the other side. So asymmetry means there's probably polarity. Let's figure out where is the dipole moment pointing in this molecule. To do that, we should look at each of the bond polarities. So let's look at this bond. Fluorine is more electronegative than carbon. So this bond is polar toward the fluorine, so is this one. But carbon is more electronegative than hydrogen. So the dipole moment, the bond dipoles of both of these guys go toward the carbon. So overall, if you add up all these bond dipoles, there's a strong dipole for this molecule going toward the fluorine side. And its neighbor down here just happens to have spun around and is oriented differently. And it has a permanent dipole moment pointing toward the fluorines. So that means that the fluorine side is going to have a partial negative charge, the hydrogen side is going to have a partial positive charge, and the dipole-dipole attraction comes from, again, these attractions of opposite charges. So these molecules are pretty significantly attracted because dipole-dipole attractions are pretty strong. Now, hydrogen bonding is basically just a really strong type of dipole-dipole attraction. Hydrogen is not very electronegative at all. So if it is bonded to an atom that is highly electronegative, the result is bonds that are highly polarized. And we end up with a highly partial positive charge on the hydrogen and a significant partial negative charge on the electronegative atom that the hydrogen is bonded to. So notice that oxygen, fluorine, and nitrogen are the three most electronegative atoms. So when you have a hydrogen bonded to either one of these elements, you have the potential for hydrogen bonding. So these two methanol molecules are strongly attracted because there are highly partial positive and negative charges on these atoms. And so these are actually hydrogen bonds, so we can write a little dotted line to show that there are hydrogen bonds between the oxygen and the hydrogen. Don't get these confused with ionic bonds or covalent bonds. They're different.
Made with Doodlecast Pro.